Hello and welcome back to Complex Analysis. And first I want to thank all the nice people that support this channel on Steady, via PayPal or by other means. Now in today's part 2 we will talk about the complex differentiability of functions from C to C. This means that the input and the output of the function f is given by complex numbers. Now you might recall from real analysis that first, differentiability is a local property. This means when we ask the question if the function f is differentiable at a given point z0, it only matters what happens around this point z0. And for that reason, the domain of the function f does not have to be the whole complex plane. It can be any open set U in the complex plane. Hence, if you visualize the complex plane like this, you can just mark any region here. For example, our domain U for the function f could be this set here. It could look as strange as you want, the only important thing we need is that it is an open set. Now of course, the natural question now should be, what is an open set for the complex numbers? Hence, this is the first thing we now want to define before we talk about the definition of differentiability. Now I can tell you, this definition is the same for all metric spaces. And please recall, a metric space is a set where you can measure distances. In C, the complex numbers, we can do this, and of course we can also do it in R, the real numbers. Therefore, this definition is exactly the same as I showed you in my real analysis course. Nevertheless, it's good to refresh your memory, because this notion is used throughout this course. Indeed, openness is not complicated at all, and to get an idea, let's take our set U from before. Visually speaking, this set should be an open set if these boundary points you see here are not part of the set U itself. In other words, if you are a point in the set, then around you only see points of the set U. To put it more precisely, a whole epsilon ball around Z lies in the set U. And if this works for every point from the set U, we call U open. So formally, we would write for all Z in U, there exists an epsilon ball. And here you already know from the last video, the epsilon ball is denoted by B epsilon Z. And now our claim here is this epsilon ball lies completely inside the set U. Okay, so this is openness for subsets of the complex numbers. One important example is of course the complex plane itself. Also, it's easy to show that every epsilon ball is open with this definition. Okay, other useful and important examples we will see later. Here, first, as promised, we want to talk about differentiability. However, now the function f we consider has a domain we call U. So it's still a complex function, but now with a general open domain U. And now, to write down the definition of differentiable at a given point, we have to fix this given point. So we have z0 as a point in U. Hence, then we are able to define what it means that the function f is differentiable at z0. And often, to make it clear that we are talking about complex functions here, we say the function is complex differentiable at the point. However, the meaning is exactly the same as for real functions. We just want a linear approximation around this point, which means the slope at this point should exist. And of course, a slope we usually calculate with a difference quotient. So we have the difference in the output divided by the difference in the input. In other words, what you see here is the slope of a secant. And in order to get the slope of the tangent, we have to consider the limit. Hence, z goes to z0 and this limit should exist. And in fact, this is the whole definition of complex differentiability at a given point z0. However, I think I should say a few words what this limit means here. Of course, as often the formal definition is the same as for real numbers. However, we immediately find different consequences when we deal with complex numbers. Before we discuss them, let's first look at the definition here. The definition of the limit means that we consider all sequences Zn in the set U, but they shouldn't take the value Z0. However, they all should converge to the point Z0. Now, for each of the sequences Zn, we get a new sequence here. And of course, the claim here is that this new sequence here also converges. And also, the limit we get out here does not depend on the chosen sequence Zn. We always get the same number out. So please remember, this is just the meaning of this symbol here. Indeed, in real analysis, we have exactly the same definition. However, there you can split the limit into two parts. You could approximate this from the right-hand side or the left-hand side. Because in R, in the real numbers, we have an order. And you already know, we don't have an order in C. Indeed, if we want to converge into this point Z0, we have a lot of directions. So you immediately see, with all these directions, this limit here is more complicated than the real differentiability we have in real analysis. So it looks the same, but here we immediately have a two-dimensional problem. Okay, I would say how all this is related to the linear approximation as we have it for real functions we will discuss in the next video. And then we also look at examples, and then you will see why complex analysis is so interesting. Therefore, I hope I see you there and have a nice day. Bye.